Last thing we're going to look at in this chapter of combinatorics is what we call the pigeonhole principle. This is basically the idea. If you've got n plus 1 or more objects, but you've only got n places to put them, so traditionally they call it, oh well, we've got n plus 1 pigeons and n pigeonholes, then if we're going to put all of them into a hole, there must exist at least one of the holes must have more than one pigeon in it. Because how else would you put n plus 1 into n? Not going to fit. Right? That's the basic idea. Now, we're going to do a little proof of that here. So what we're saying is, k is going to be the maximum number of objects I can put in n holes without having more than one object in a hole. I'm going to prove that k is actually less than n plus 1. Okay. But I'm going to do it by contradiction. Remember that idea of proof by contradiction we looked at with that? I'm going to use the same. So I'm going to assume the opposite. I'm going to assume that we could actually put more than n objects into n holes. So k is going to be greater than or equal to n plus 1. So we know the maximum number of objects would be n. Each hole would have one object. So therefore k is less than or equal to n. But I just assumed that k was greater than or equal to n plus 1. So I get my contradiction straight away, really. Thus, it can't be true that k is greater than or equal to n plus 1, so k must be less than n plus 1. And if it's less than n plus 1, that's the same as saying less than or equal to n. Anyway, let's generalise it. The actual generalised one's this, is if you have kn plus 1 or more objects that you have to put in n holes, then at least one hole must contain k plus 1 or more objects. Let's do some examples. It might make more sense when we see what we're doing. So we've got 6 integers and we're going to select them from this set of numbers, 3, 4, 5 up to 12. How many of those integers do we need to select to ensure that there's a pair of numbers that add up to 15? So the first thing here is we've got to work out what are the pigeonholes. And the pigeonholes are the pairs of numbers that add up to 15. So there's going to be 5 possible pairs. So one of my holes would be 3 and 12. One would be 4 and 11. One would be 5 and 10, one would be 6 and 9, one would be 7 and 8. And the question now is, how many integers do I need to select to ensure that we have a pair of numbers that add up to 15? So here's how we do it. N is equal to 5. That's the number of holes that I've got. Okay. Now, the pigeonhole principle tells us that 6 integers need to be selected. So we need to have at least one more to ensure. So they would be the objects. Okay. What does it mean? Because think of it this way. I'm going to pull out the integers. If I pull out just 5 integers, I might have pulled out 12, then 4, then 10, then 6, then 7. I don't have a combination there that adds up to 15. But once I have one number from each of these, then all I need is one more number. And I must get a pair somewhere that adds up to 15. So I need one more than the number of holes. Let's look at this one. 50 points. We're going to put them in a 7 by 7 square. What's the maximum distance apart the 2 closest points could be? Well, this square I could divide up into 49 1 by 1 squares. And so we've got a big square, 7 by 7. Right. So I'm saying there's 49 holes. Well, you can even imagine it. You've got a square, and you can even imagine seeing all those holes. If I divide it up, each one of those little squares would be the holes we're going to put things into. Now, the pigeonhole principle then tells us that 50 points, if I've got 50 points, there must be at least one square in there that contains 2 points. Actually, I could put one in each of the 49, but then the 50th has got to go into one where one of the other ones is. Okay, so they're the objects that I'm placing, the 50 points. Where would I put them inside the square? Well, I know that inside an individual square, the closest distance between the points would be a maximum when there's only 2 points in the square. So I'm looking at that square now that has 2 points in it. And the question is, what's the maximum distance apart the points could be? Well, we know those two, if they were sitting on the end of the diagonal, that would be the furthest apart they could be. Because if I was to place them anywhere else, they'd be closer than the length of the hypotenuse, and we know the hypotenuse is going to be the greatest side of a triangle. So a little bit of Pythagoras there, I can work out the square root of 2. So the maximum distance, the closest pair of points, so the closest pair of points would be the 2 points that are in the same hole. Okay? And we want to know what's the furthest apart they could be. Well, I'm trying to fit these 2 points in a square so that they're the furthest away they could be. And they would have to sit on either end of the diagonal. And so that's what I've worked out there. Well, what's the length of that diagonal? It's the square root of 2. We've got a group of n people. There are always going to be at least 2 people with the same number of friends in that group. So someone might have no friends, someone might have 1 friend, someone might have 2 friends. But you could always find that within a group of n people, and we're just talking about friends within that n, so not friends that are overseas or something like that. So within that group of n, there will always be 2 people with the same number of friends. Okay. It's not going to be possible for one person to have no friends and another person to have n-1 friends. That would be impossible. Remember, there's n people. And obviously, I'm one of the people. So therefore, if I have n-1 friends, that's everyone else. So it would be impossible for someone to have no friends. And the reverse is also true. If there's someone there with no friends, it would be possible then for someone to be friends with everybody in the group. Okay. So therefore, whether I think of it as no friends is not possible or n-1 friends is not possible, we know there's one of those situations won't happen. So I'm going to discount the unfriendliest possibility where there is someone with no friends. Okay, that's not going to happen. So it's possible then that people could have 1 friend, 2 friends, 3 friends, all the way up to n-1 friends. So there's n-1 different number of friends a person could have. They're the holes. I'm going to allocate the people now to each of those. So I'll grab this person. Which one will you go on top? Oh, you've got 2 friends. Okay, I'll put you sitting on top of 2. This person, oh, you've got 3 friends. Oh, you'll sit on top of 3. But if there's only n-1 possibilities, and I've got n people, even if I go through the first n-1 and they will have a different number of friends, that nth person is now going to have the same number as one of the people I've already allocated. Because there's more than the n plus 1. So by that pigeonhole principle, we must end up with at least 2 people with the same number of friends. 16 positive integers are written on the board. Okay. At least how many numbers will leave the same remainder when divided by 5? So I've just randomly picked 16 positive integers. They could be anything. But there must be at least how many numbers that will leave the same remainder when I divide by 5? Okay. There are 5 possible remainders. 0, 1, 2, 3 and 4. So they are, if you like, the holes. Because I'm going to get these random numbers and I'll allocate them to what the remainder is. Oh, this one has a remainder of 2. This one has a remainder of 3. And so on. So if I've got 5 possibilities, so they're the holes, then 5k plus 1 is 16 in this case. K would equal 3. Remember, the pigeonhole principle, the generalised one, said kn plus 1. Right? Objects. We've got 16 objects. So that's kn plus 1. N's the number of holes. So sub that in. K equals 3. I've got my result. So we must have one more. So at least 4 numbers will have the same remainder. Right? So if I just put 16 random numbers on the board, at least 4 of those will have the same remainder when we divide by 5. And I don't care which 16 you pick. Has to happen. The pigeonhole principle. So what we had to do here was identify the holes, that was n. If we have kn plus 1 objects, so the number of objects is kn plus 1, placed into n holes, so the holes is n, then at least one hole must have k plus 1 objects. So back to our problem. So we identified that the number of holes, the possible remainders, was 5. Kn plus 1 was the number of objects we had, 16. From that we can work out k is 3, so we know there must be k plus 1 objects. So k plus 1 leaves us with 4. So we knew there had to be at least 4 numbers that would give the same remainder. This is quite an interesting one. A computer is going to generate random 3-letter words. Let's just generate random 3-letter words. How many words do we need to generate to ensure that in our list of words there is a word that has been generated 8 times? Generated 8 times. So what do we know here? Well, we can work out using our counting idea, our basic counting principle. We know the total number of possible words is 26 cubed. Because I'd get a letter, then another letter, then another letter. So 26 by 26 by 26. So the number of holes in this case is 17,576. So we could generate one of those 17,576 words. So it's going to generate a word and we just basically place it in the appropriate spot. We want a word to be generated 8 times. So we know in this case the result has to be 8. So k plus 1 has to be 8. So k is therefore 7. So kn plus 1 is the number of numbers I need to generate. So the number of objects. So it'll be 7 times 17,576 plus 1. So if we generate 123,033 words, then we can guarantee that one of those words must have been generated 8 times. So there's our answer. 123,033 words need to be generated. Right. So this is what we call the pigeonhole principle. Right? So the very simplest version is when you're saying, okay, I'm going to place n plus 1 pigeons in n holes. There's always going to be a hole with 2. But the generalised one becomes far more useful for interesting problems. But you need to identify what are the holes, what are the pigeons, and then what's the result. So it'll be one of those things you'll be trying to work out.